In this video, I'm going to teach you about momentum and elastic collisions. During an elastic collision, there is no loss of kinetic energy from a system. In other words, if you were to compare the kinetic energy for the system before and after the collision, those values would be the same. In nature, we see perfectly elastic collisions solely on the atomic level. However, there are numerous systems on a macroscopic level that can also be classified as elastic collisions. For example, this Newton's cradle is an example of an elastic collision in which the kinetic energy for the system is the same before and after the collisions. Now, there is some negligible amount of energy that is being dissipated from this system, as it will eventually come to rest. However, it is a very close approximation to an elastic collision. So in this course, you will be asked a number of times to classify whether a collision is elastic or not elastic. And the key to these problems is understanding that during an elastic collision, not only is momentum conserved for a system, but so is the kinetic energy for the system. Let's look at this example I spoke to you about in a previous video on the conservation of momentum. We have these two objects initially about to collide. If we consider their respective masses and velocities, we can calculate the kinetic energy of this system before the collision. Now recall that their masses were the same at 0.5 kilograms. Also remember that now we're dealing with energy. Energy is scalar. Also recall from the previous unit that when we plug in our velocity values, and those are indeed vector quantities, however, because those values are squared in the kinetic energy equation, we're always going to get a positive value for kinetic energy. Now let's look at after these two objects collided. And again, if you plug in their respective masses and velocities into these equations, you will get 0.5 joules both before and after the collision. Therefore, this particular collision would be classified as an elastic collision. Let's look at a more complicated problem. In this PHET simulation, two objects are going to collide. We'll define our system to include both objects. In this problem, you're being asked first to determine whether or not this particular collision is elastic. So what that means is you are being asked to compare the initial kinetic energy for the two object system to the final kinetic energy of the system, which means you'll need to take the individual kinetic energies before the collision and add those together. In other words, we're going to sum the initial kinetic energy, putting in the respective values for both mass and velocity. Before the collision, we can find the kinetic energy of the system to be 0.42 joules. And employing this same methodology after the collision, we can find the kinetic energy for the system to again be 0.42 joules. Because these two values are the same both before and after the collision, it can be stated that kinetic energy is conserved. Kinetic energy is remaining constant, and therefore we can classify this collision as elastic. In the next part of this problem, we're being asked to compare the energy and momentum, specifically looking at the transference from one object to another object within our system. This accentuates the importance of looking at not only a system, but also looking at individual objects within the system. In the last video, I taught you that momentum was conserved for an isolated system. However, individual momenta for objects within that system could change. So let's go ahead and look at what's occurring for the energy between ball 2 and ball 1. If we look simply at our speed for the light blue colored ball before and after the collision, we can see it has gained magnitude of speed of velocity after the collision. Now, you may also note that it has changed directions. It was originally moving to the right. Now it's moving to the left, and with a much greater magnitude of velocity. In other words, its speed has increased from 1 to 1.9. If we calculate the kinetic energy initially for ball 1, right here, do this calculation, and you'll find it to be equal to 0.05 joules. If you then do this calculation for the light blue colored ball after the collision, its kinetic energy has gone up to 0.18 joules, which means the magenta colored ball has transferred 0.13 joules of energy to the light blue colored ball. Go ahead and pause the video, do those computations to confirm, and you will see that that is how much energy has been transferred from ball 2 to ball 1. The last part of this, we're looking at the momentum. We're looking at, in other words, at the impulse, which means we're going to calculate the change in momentum for the light blue colored ball, or ball 1. And we're going to take the final momentum and subtract the initial momentum, and we're dealing with a vector quantity, so we need to pay attention to the signage. We can find that to be negative 0.29 Newton seconds, which means 0.29 Newton seconds of this leftward momentum was transferred from ball 2 to ball 1. Momentum for the overall system, however, remains constant both before and after at negative 1.4 Newton seconds. Again, pause the video, do this calculation to confirm. Let's now look at this problem in which a 60-gram tennis ball collides elastically with a wall. So I am going to underline the word elastically, which is very important. So the object comes and strikes the wall, reverses direction, and now you're being told that that collision is elastic. What that means is the object's initial kinetic energy is the same both before and after the collision. This problem is asking you now to calculate first the change in momentum for the tennis ball. So taking the final momentum and subtracting the initial momentum and paying close attention to the signage for these vector quantities, we can find that the tennis ball's change in momentum is 0.6 Newton seconds to the left, or negative 0.6 Newton seconds. I want to now look at this in relative terms. On many of your assessments, you will not be given values. Everything will be done relatively. In other words, you'll have an object of mass m is initially moving with a velocity of v, strikes a wall, rebounds with a velocity of negative v. What is its change in momentum in terms of its mass and velocity? Okay, so in order to do that, we've set up the problem identically. So we have paid attention to our signage here, except now when we solve this problem, we get an answer of negative 2 times mass times velocity, which is interesting because if you pause the video now and calculate this object's initial momentum, you'll find it to be equal to 0.3 Newton seconds. Yet its overall change in momentum is twice that in magnitude. It's 0.6 Newton seconds, and in fact, it's in the negative direction, which makes sense because the object's momentum is to the left after it strikes the wall. So this is also an important and powerful calculation to be able to do in relative terms of mass and velocity. Lastly, let's look at how much kinetic energy it has after the collision. Well, whatever it has after the collision is the same as what it had before the collision, because this object strikes and collides elastically with the wall. So we can calculate the final kinetic energy for the object, and it is equal to 0.75 joules, which is exactly what its kinetic energy was before it struck the wall. In this video, I've continued to speak to you about momentum, and I've now defined an elastic collision as a collision in which not only momentum is conserved, but kinetic energy for the system is also conserved. And I'll see you guys in class.